Hello everyone, this is chapter 3, describing data visually. In this chapter, we shall talk about different ways to describe and present your data with the graphics and charts. There are basically two methods of organizing, exploring, and summarizing data. One is visual, using charts and graphs that provides insights into characteristics of a data set without using mathematics. The other is numerical. We are using statistics or tables that provides insights into characteristics of a data set using mathematics. For visual description of data, we need to begin with let's begin with univariate data. That is a set of n observations on one variable, and we need to consider the following. First is measurement. What are the units of measurement? Are the data integer or continuous? Is there any missing observation? Any concerns with accuracy or sampling methods? Then there's a central tendency. Where are the data values concentrated? What seems to be typical or middle data values? Then dispersion. How much variation is there in the data? How spread out are the data values? Are there unusual values? And then the shape. Are the data values distributed symmetrically, skewed, sharply peaked, flat, or bimodal? Let's start with the visual description of data by using dot plots. First, we need to sort data. For example, on slide number 4, this is the price-earning ratio of some companies. In case you're not familiar with that, the P ratio or price-earning ratio is the stock price of a company divided by its annual earnings or net profits. We first need to sort the data and then summarize it in a graphical display. The data you can see in the table 33.2 start with 8, there are 2 8s, 1 9, 1 10, lots of 11s, and etc. The last one is 29. And then we can graphically display the sorted data using a histogram called dot plots. Basically, they plot each data value as a dot above an appropriate scale. On next slide, slide number 5, you see the dot plots. This actually shows the data, the dispersion of data, so the range of data. And the clusters shows the central tendency of the P ratios. Dot plots, keep in mind though, do not tell much of the shape of the distribution. You can see this to the left is Occidental Petroleum, and to the right is Roman Hess Company. Each blue dot represents a company. You can add annotations, such as company name, text boxes, to call attention to specific features. You can also stack dot plots when you compare groups. A stacked dot plot compares 2 or more groups using a common x-axis scale, like this one, showing the median sales price of single-family homes in different parts of the United States, Central, Northeast, Southeast, and West. You can see in the West Coast, the home price, median home sales price, is much wider spreaded than that in Northeast, and than the Southeast. And the central part of the country, you can see the home prices are closely, net together. And let's talk about the histograms or frequency distributions. In the frequency distribution is a table formed by classifying n data values into k classes, or we call each class a bin, so into k bins, right? The bin or class is a one peak on one column in the histogram. The bin limits define the values to be included in each bin. The width must all be the same, right? So we can have equally wide equal wide bins across the data range. Frequencies are the number of observations within each bin. And we can express that as a relative frequency, that's frequency divided by the total, or percentages, that's relative frequency times 100. Now, how many bins should we have? Okay. There is the there's the Sturgis rule in deciding on the number of bins to have in constructing a frequency distribution. Basically, if you look at the table on slide number 8, you see we started with sample size 16. The suggested number of bins or groups should be 5. In other words, we divided 16 observations, 16 numbers into 5 groups. If it's up to 32. If you have 32, a sample size of 32, you should have 6 bins. 64, you should have 7 bins, etc. You can actually memorize this table easily by just remembering the two numbers, 16 and 5. With each one increase in the number of bins, from 5 to 6 to 7, 8, up to 11, you can see the sample size doubles, from 16 to 32 to 64, 128, etc. And the frequency distribution of PE ratios using 6 bins is on this table. Right? You can see the bin limits is from 8 to 12, the frequency is 10, meaning for the PE ratio between 8 and 12, there are 10 companies in that category. Since there are a total of 57 companies, 10 over 57 gets you the relative frequency of 0.754. And cumulative frequency, of course, is still 10 because this is the first group. And cumulative relative frequency is still 1.1754, this first group. Then the second bin from 12 to 16, there are 14 companies. Then the relative frequency is 14 divided by 57, you get a 2456 right here. And the cumulative frequency is 24. How do you get 24? You use a 10 plus 14 to get 24. And the cumulative relative frequency is 0.4210. How do you get that? You use a 24 divided by 57, you get 0.5210. Okay? And so on and so forth. You can calculate all the relative frequencies, cumulative frequencies, and cumulative relative frequencies. Cumulative relative frequencies have always adds up to 1.0 because that's all the companies that, of course, the cumulative frequency is 57, that's total over 57, then that's 1.0 or 100%. The histogram then is the graphical representation of a frequency distribution. You have the data, you have the table, you have divided them into groups, now you can construct that. The y-axis of the histogram shows the frequency within each bin. And the histogram is a bar chart. In case you use the Excel to do that, you see it's a bar chart. And x-axis the text of x-axis shows the endpoints of each bin. These are the 3 histograms for the PE ratio data with a different bin width. The first one is with 5 bins, middle one with 8 bins, and the last one with 11 bins. Right? Which one, what do they tell you? You probably can tell, see, there's not too much information told with 5 bins. There's more information told with 8 bins. And with 11 bins, you can see more of variations, more peaks, more, more groups involved. Okay? Now let's talk about the model class. A histogram bar that is higher than those on either side is a mode. Right? If there's a one single model class, we call it unimodal chart. If there are 2 model classes, we call it bimodal. You have more than 2 model classes, we call it multimodal. Model classes may be artifacts of the way bin limbs are chosen, because as you can see in the previous chart here, with 5 bins you see only one mode. With 8 bins you see one mode as well. And then with 11 bins, how many do you see? You can see there's a 1 here, 2, 3, and 4. Some may argue this could be another one. Okay? The shape of the chart or histogram. A histogram suggests the shape of the population. It is influenced by a number of bins and bin limits. And we need to learn a new term called skewness. Skewness is indicated by the direction of the longer tail of the histogram. If the longer tail is on the left, we call it left skewed or negatively skewed. If the longer tail is on the right, we call it positive skewed or right skewed. If both tail areas approximately are the same, we call it symmetric. As seen on this chart here, this one, longer tail is to the left, skewed to the left, is left skewed. This one, longer tail is to the right, is right skewed. And this one is symmetric. And this one shows the 2 modes skewed left. And this one shows the 3 modes, trimodal, symmetric. This one, 2 modes skewed right. Again, this one is skewed left, but you can see there's some observations of the way up to the far left. We call the outliers. So this is skewed left with outliers. This is symmetrical with outliers on both sides, and this is skewed right with some outliers to the right. Frequency, polygon, and algorithm. Okay? We can connect the dots. Basically, at a P ratio at different frequencies, if we connect them, we show this polygon. We call it frequency polygon, showing the frequencies. And the algorithm is basically like a cumulative frequency polygon. So every point, you add up the frequencies of previous observations, previous bins, you keep going up. Therefore, in the algorithm, in the end, the cumulative percentage will always approach 100% right here. See? Now let's talk about the line charts. Yeah. Basically, we can use simple line charts to display a time series or spot trends or compare time periods. And it can display several variables at once. This one chart here shows the monthly basic rate of cable TV between 1975 and 2005. And at x-axis, you can see the years from 75, 80, 85, all the way to 2005. There's dollars per month on the cable charge. What do you think? This one shows the time series data. It shows the trends. So you can see between 1975 and around 1985, in that 10 years period, the table rate pretty much stayed the same, between like $6 and $9, right? And then starting in 1985, it starts to grow up, right? And basically on the upward trend all the way until today, out to the $40 a month. And that's a pretty sharp increase over the next, 20-some years. You can use a 2-scale line chart like this one. Basically, you can use to compare variables that differ in magnitude or are measured in different units. Like this one, the cell phone statistics. Cell phone between 1995 and 2005. The scale on the left is dollars per month. That's you can see here the average monthly bill is in blue, and the scale on the right is the minutes per call. That's the kind of like red or maroon letter, maroon colored. It's the average call length of call. Okay. Interestingly, you see the monthly bill has always been going up somewhat, right? Gradually going up, and the average length of a call first, was pretty high, then dropped. Here, that's around the 3.2 minutes, dropped down to like around the 2.4 minutes, and then gradually picked up. So that's an interesting phenomenon, we can investigate. Another line chart is one with the grid lines. You can, that's a grid line graph usually has no vertical grid lines. Horizontal lines can be added to make it easier to establish the Y value. So you can see, look at this value here, this point here, with grid line you can see is clearly between 800 and 1000, right? But which one of the two is easier to read? You can see probably this one is easier to read, but this is probably too much, too condensed. This is probably easier on the eyes, right? This shows the annual utility cost between 1980 and 2006 in dollars for electric utility, gas, and water. Okay. You can most charts we construct, we use the arithmetic scales. The distance on the y-axis is proportional to the magnitude of the variable being displayed. But often, sometimes we may use a logarithmic scale. There's a ratio scale. The equal distance represent equal ratios. Use log for vertical axis when data vary over a wide range, say by more than an order of magnitude. Really big changes, and that is when a log scale is preferred. Like this chart, two charts here. The chart here on the right. The chart on the left is the arithmetic scale. You can see that, right? And for the same chart, same data, you put it on a log scale. It's from 10,000 to 100,000, from 100,000 to a million. You can see this is 10 times. There's another 10 times, but it's not the equal arithmetic scale. But for this time data, this may be preferred by some analysts. You can also use bar charts, plain bar charts. That's the most common way to display attribute data. Bars represent categories or attributes. The length of bars represent frequencies, like this one here. This is the US-Canada light vehicle tire market share between the different brands: Goodyear, Firestone, Michelin, General, BF Goodrich, Bridgestone, Uniroyal, Continental, and Dunlop. Right? This is the percentage of market share. You can see Goodyear clearly has a market leadership that's much higher, twice more higher than the next three competitors. Or you can put in a horizontal one, like this one. I don't know which one you prefer, but seems most students cannot prefer this one, horizontal bar chart. You can also do 3D or novelty bar charts, like this one here. This is a 3D bar chart. Remember, this is the same market share data for different tires, and the third dimension going into here, this one, going into the paper, into the screen, is meaningless. We just make it look nice and fancy. So it's kind of a novelty chart. Okay? Or you can put them as a pyramid, to show the same number, same data, same thing. We can also do some Pareto charts. That's a special type of bar chart that's used in quality management to display the frequency of defects or errors of different types. Like this one showing the body shop defects, right center, right door, I don't know what the RP post is, like different parts of the body location and a number of defects. And then using Pareto charts, you can identify the most frequently occurring problems with your parts, so you can focus on your way to improve the quality with that. Okay. Then you can have a bar chart stacked. This one, the stacked bar chart, the bar height is the sum of several subtotals. Areas may be compared by color to show patterns in subgroups and total. This shows the medical school application by gender. The maroon is for man, blue is for woman. You can see the application by women are increasing slowly, okay? And the application by men are increasing a little bit faster, seems, right? This shows the comparison of genders also over the years. You can use bar chart for time series data. And this is, as we have seen before, this is the monthly cable rate. You can use the line chart, or you can use bar chart. They pretty much convey the same meaning. You can do scatter plots. Scatter plots. That is with two variables, you can use scatter plots that can convey patterns in data pairs that will not be apparent from the table. Like if you have two variables, x and y, right? If you plot x versus y for each one value of x, there's a corresponding y value. You plot one point, and you go over this on all the data points you have. If you see a pattern, a chart or a plot like this, we call this a strong positive. We'll talk more about this later on. It's positive meaning because x goes up, seems to be y is going up as well. That's why it's going up like this. So, and this is strong meaning the dots are closely held together. Okay? If it goes, instead of going up, it goes down, we call it strong negative. It's very strongly holding together as well. In this case, we call that the weak positive. It's positive, all right. You see that when x goes up, y goes up as well, right? But they are not closely knit together. Kind of like loosely knit together. So that's why we call it a weak positive. This is a weak negative. And in this case, there seems to be no pattern between x and y. And this one seems showing a nonlinear pattern. It goes up and then it goes down. Okay? We talk about this when we talk about correlation and regression. Okay? Tables. Tables are the simplest form of data display. A compound table is a table that contains time series data down the column and variables across rows. For example, school expenditures. Right? A range of data is in rows and columns to enhance meaning. The data can be viewed by focusing on the time pattern down the columns or by comparing the variables across rows. Like this one, the school expenditure. This one shows the years 1960, 70, 80, 90, 1990, and 2000. They show all the schools, the expenditures in millions of dollars, I believe in millions of dollars, in billions of dollars, sorry. And also shows by elementary and secondary schools total, and the public schools and private schools. And then by colleges and universities, total, public, and private. Okay. Pie charts. The pie chart that's often abused, right? A pie chart can only convey a general idea of data. Pie chart should be used to portray data with sum to a total. That's why, for the whole pie, and then we can divide the pie, right? So the slices of pie. A pie chart should only have a few slices, 2 or 3 maybe. Don't have too many. Each slice should be labeled with data values or percents, like this one. Consider the following charts used to illustrate an article from a Wall Street Journal. Which one is better? Okay. This one shows where did you buy your statistics textbook for students, right? If you're using this pie chart, you can see, the majority of them bought the book from campus bookstore, 54%. Some bought from the web, some from retail outlet. Another student from another student, 3%. Now this pie chart nicely shows where students got their textbooks. Or you can use bar charts like this. Which one do you think is better? I would say, probably this is better. It's more intuitive, more clearly showing the numbers. Okay. Pie chart options. You can actually have an exploded pie chart and 3D pie chart. This is an exploded pie chart. Kind of like the pie slices are removed a little bit, kind of exploded, right? It's nice to show that. Or you can make the 3D. The third dimension, the height of the pie, is meaningless. It's just make it look nice. Okay. Embellished pie charts. That's a chart created in Excel. You can add a lot of things. You can edit to improve the titles. You can change the axis scales, right? You can add a data table underneath the graph. You can change color or patterns in the plot or chart areas. You can format the decimals into a lot of things. Okay. And the chart created in Excel can also be added to alter the appearance of the bars. But be careful, do not over-embellish your chart. Doing too much is not good. Excel does offer many other types of specialized charts, such as a radar chart or spider chart. It's used to compare individual performance against the benchmark. But there are some deceptive graphics that I want you to be aware of. Error 1 is non-zero origin. A non-zero origin will exaggerate the trend. Look at this one, the average length of cell phone calls. If you start with 2.1 instead of 0, you see there's a huge variations among the length of cell phone calls from 1999 to 2005. But if you use zero origin, you can see there is change, but the change is not that dramatic. So this is deceptive, this is correct. Error number 2, elastic graph proportions. If you keep the aspect ratio, that's the width and height, below 2.0 so as not to exaggerate the graphs. By default, Excel uses the aspect ratio of 1.8. You can see this one is stretched and therefore it's more flat. This one is squeezed, therefore it's a steeper slope. Neither is good. Error 3 is use a dramatic title to attract people. That's not good practice. Error 4 using distracting pictures. That's not good. Error 5 using authority figures. You can use pictures of authority figures to impact credibility to self-serving commercial claims. Error number 7 is missing axis demarcations. You did not mark them. Error number 5 is missing measurement units or definitions. They are not good. Error number 6 is 3D and rotated graphs. If you look at that, if you have a 3D chart like this one, it could be deceptive because it makes the trend appear to dwindle into the distance or loom larger towards you here. Right? The correct chart is like this. You see, the changes are not that dramatic. Complex graph, error number 10. Avoid if possible. Keep your main object in mind. If necessary, break graph into smaller parts. This one have too many categories and too fragmented slices of pie. That's not good. Error 11. Gratuitous effects. Avoid too many annoying special effects when using slide shows. Number 12. Estimated data. If you have estimated data points, you should note them. It should be noted when used or avoided if possible. Error number should be number 13, vague source. And that may indicate the loss of citation and non-source or mixed data sources. Use complete source citations. Error number 13 is the area trick. Sometimes as the figure height increases, in this case, so does the width, therefore distorting the area. You increase the height, the bar, the height, the frequency changes from year to year, and if you increase the width of the bar as well, and then it looks much bigger than previous years. Well, in fact, when in reality, it does increase, but not as significant as shown in this chart. Okay. And that's it. That's all we have for chapter 3. Thank you.